Hello and welcome back. In the last set of videos, we're going to look at the level sets based image segmentation algorithms. Specifically, we're going to look at something called the geodesic active contours, which is an improvement to the snakes model we saw earlier. And then we're also going to look at the Chan-Vese segmentation, which is derived from the Mumford-Shah function. Okay, so what is the problem with the snakes algorithms that we saw earlier? Is that self intersections will eventually happen. Um, Also, when we initialize the contour, it doesn't automatically split into different parts if there are multiple objects in the image, right? So a priori, if you know, let's say if you have 5, 6 objects in the image that you want to segment, then we need to initialize 5 or 6 independent contours. So automatically splitting and merging of contours doesn't happen. Okay, and in general, convergence to local minima will occur because of the gradient term. There are going to be quite a few noisy pixels in an image, and eventually those will contribute to the local minima. So that problem is always there, right? But advantage is that you can incorporate pair shape knowledge. We'll look at this in the next class, next week's of lectures. Next week lectures, and you also have the advantage that you only have to track a limited number of points, even for very large images. So that's a advantage. However, the biggest problem is the convergence to local minima, as well as are difficult to program in terms of keeping track of the contours so that it doesn't intersect with itself, and also if you want to split and merge if there are multiple objects in the image. So this is where the level sets representation comes in. So what we do here is that we embed the curve that we are trying to propagate into this level set function, typically denoted by phi. Okay, and we actually evolve the level set function. That is, the function is evolved to propagate the curve. But how is it different? Here we are actually changing. If you think of the phi as a function, then we are changing the value of the function at every point. Okay, but in the snakes model, we are actually displacing the point itself, right? So that's a big difference between the two. So we'll look at what that means in the next few slides. But in general, what we do is we will embed the curve in the function f phi. So how do we embed the curve in phi? We will embed it as a zero level set. Okay, or typically it's a zeroth level set, right? So phi is like, think of it as a function which has values everywhere. In the sense, if you discretize it, you can think of it as a 2D grid, same size as the image, and has equal number of pixels as the image, and every pixel has a value, and we embed the curve in that function by setting those pixel values to 0 that correspond to the curve. Okay, that's typically how it's done. So for instance, typically I'll just give you a very small demonstration here. So I'll just use this. So for instance, if you have this, let's say this is the original image size, right? So and I'm just going to make this into a small grid. So if you have a curve which is something like this, okay. So typically you would, in an image, you would keep track of discretize this curve and keep track of these individual points, okay, and then move them, and then you would displace those points, and those points, as you saw earlier, would be displaced so as to make sure that the curve overall is smooth, and also that it gets closer to the edge of the image. So it will be driven by the image forces. So in the case of, this is your typical this is your snake's representation, right? Where you have, now when you talk about let's say level set representations, let's just redo this. It's very simple. So what we would do is set to 0. So this evaluates so this is the function phi of x, right? Actually phi of x comma y, but we'll just use phi of x as a vector. Okay, same thing. So you will set the values to 0 of this function wherever there is a curve. Okay. So approximately that what we see here. Okay. And you would evolve phi of x comma y. This is evolved. So the value of this function will change. So then how we keep track of the curve is by figuring out where the function is 0, where phi of x comma y is 0, and then connecting those points will give you the curve in turn. So so going from here to there, this formulation helps in many ways, and we'll see how that helps. Because all of the problems we saw earlier with snakes, that is the self intersection, inability to split into multiple or merge, etc., those are easily solved in this context. Okay, so how do you represent the curve? So it's implicitly represented in the sense that you have to solve for phi of x equal to 0. That's what this means. Okay, so for every pixel in the image, we define the height function phi of x. So that's why the phi of x will be the same size as the image once we discretize this. Of course, here we are always talking in the continuous picture, but in the real world, when we solve the problem, the image is discretized. So phi of x will also be discretized, and for every x, phi will take on a value. Discretized value of x, phi will take on a value, which we'll call the height function. Okay, it will take on positive or negative values with respect to the curve. And we can read out the curve by reading out the pixels where phi of x makes a translation in sign. So what this means is, typically this is typically referred to as the sign distance function, but I'm going to show you a slightly easier version. So let's say I just have to draw a little bit more thicker grids so as to make this easier. Right. Okay. So if you think of it, so let's say the object. So everything inside, you would put -1. I would say inside, outside. What I mean by that slightly, and everything outside, I'm putting a same value, but typically it depends on the distance from the curve. But you would do something like this. S plus 1 everywhere, and it's -1. So your curve would be something of this sort, right? This would actually be your curve, because that's where the transitions happen, right? So, and this would be the value phi of x. So this whole image or this grid is phi of x. So for every pixel in the image, you will define a position x, and that phi of x will have a value, and it will be positive or negative depending on whether it's inside or outside the curve. And this is usually referred to as the signed distance function. Okay. So how we do that is, if you define all the zeros, if you define this as this is your initial contour, let's say you initialize it, then you know all the pixels where phi of x equals 0, and then you calculate the distance or the distance of each one of the pixels outside and inside from this curve. Okay, and that will or the shortest distance from this curve, and that is usually the sign distance function. Okay, it's abbreviated as SDF. So this is the typical representation. So I have given you a much simpler one wherein everything inside the curve is negative, outside the curve is positive, and the transition regions will tell you where actually the phi of x equal to 0 lies, and that will be the segmentation that you are seeking. Okay. So here, just to once again reiterate this point. So if you are doing the usual snakes algorithm, then you have the discretizations. I'll use a different color. So continuous curve, but you have a discretization of this curve, and you would move this curve towards the edges of the image, right? This is the edge. Let's say this is the object you're looking at. Okay. However, in the case of this level sets, the curve is represented as implicitly as phi of x equal to 0, right? All the points where phi of x equal to 0, you would connect them to get the curve. So in this diagram, so if you see, what you have done is, how do we extract the curve? Basically, here you can think of this as x and y. It's in 2D. So, and at this plane, this particular the circle here this corresponds to phi of x equal to 0. So we just have to cut at that point to get the curve, and the shape is automatically represented, right? So phi is you think of phi as a height function, right? And uh, and when you all you have to do is figure out where phi equal to 0, and that will give you the shape of the curve at any time that you want. Okay, so we look at further. So for instance, like these are some of the ways of how you can get curves different, like for instance segmentations that contain multiple objects, etc. So for instance, this red is the phi. Okay, it's here, it's shown as a height function. Okay, and then this plane where you are cutting corresponds to phi equal to 0. So depending on where the plane cuts through, you can get different types of shapes. And in fact, if you have disjoint objects, those are also particularly correctly segmented, right? So just by tracking phi equal to 0, we can just we don't have to worry about self intersections, whether we can track multiple objects, etc. But remember that phi actually tracks the curve and not the image. Okay. So so you keep updating phi based on whatever formulation you have, variational formulation you have. But in the end, extracting the curve is just by figuring out where phi equal to 0. Okay. So then we don't have to keep track of individual points in the curve. We don't have to know beforehand the number of objects, etc. Okay. So that's the level set framework. But then there are some more calculations that you have to do, in the sense some more derivations have to be done, because you are going from you're going from dx by dt, right? Dx by dt, dy by dt. Like you are calculating, you are tracking x and y points on the curve. Now you have to go to d phi by dt. You have to figure out how d phi by dt changes, so that then you keep updating phi, and then you just have to figure out where phi equal to 0. Okay, so this relationship is from here to there. What is the relationship? That's what we have to determine. Okay, so the level set evolution equations, right? So we are looking at, so far the snake's algorithm purely looks at evolution of x comma y on the curve, right? So now we are going to look at evolution of phi. How does phi change with time? So before that, let's look at some of the developments that led to this level formulation. Okay, so the displacement of the curve typically can be resolved along the tangent to the curve and normal to the tangent. Okay, see, tangent motion has no impact on the evolution, right? Because if you are moving along the tangent, then the curve stays in place. Curve doesn't shrink or expand or deform in any way. Curve just remains as it is. So the normal is typically what the displacements normal to the curve, or what actually causes the deformation of the curve, and also for the curve to move. Okay, so the normal displacement we will typically attribute it to some speed function f. Okay, and we can actually write the curve evolution equation as dc by dt equal to f times n cap, where n is the normal, which is outward pointing, or in some cases inward pointing normal. So this is what I was talking about. So if you look at this set of contours, okay, the normal, let's say at any point, will, let's say, point in this direction, okay, and the tangents will be there. So let's set a point by point. So you can look at it at different points. Okay, so along the tangent to these curves, there is no motion. Only along the normal you have some kind of component of the motion. Okay, then let's try to relate how how this phi changes corresponding to how x comma y move. Okay, so if we consider a point x comma y, we're only going to do 2D, right? So we don't have to worry about 3 dimensions, but it can also be done in 3D. So we consider x comma y, right? A point on the curve, point on the segmentation contour. Try to see how it evolves and related to how phi will evolve. Okay. Now we know that we already stated that phi of x equal to 0 is what determines the contour. Correct. So wherever the segmentation contour is present, phi at that point, those points will be 0. So if x comma x of t, so we know that we evolve this in time. So x of t is position over time, right? This position over time. Here this means that we are evolving the contour under the influences of several forces. We saw that there is one due to the gradient, others due to the regularization terms. So this so phi of x equal to 0 is our segmentation contour. So that will directly translate to phi of, this is true, right? Because this is our segmentation. Um, that's what we want. So this is the 0th level set, and it always gives us the contour. Okay, it doesn't matter what shape it is. We just want to make sure that when we extract phi equal to 0, it is the contour. Okay. So if we know phi at t equal to 0, which is possible because we always initialize the contour, then at any time t, right? Any time t, we know that d phi by dt equal to 0. I'm excluding um, the explicitly a dependence on x, etc. Okay. Here, okay, when I say x comma x of t, I meant x comma y, right? I can also write phi of x of t, y of t, right? This is the thing. Okay. So if d phi by dt equal to 0, where I suppress the dependence on x and x of t and t, then using chain rule, we can write this as, so we'll write this as delta phi delta x delta t plus delta phi t. Sorry, this is d phi by dt equal to 0. Okay, t equal to 0. Okay. Now this actually translates to what? This will actually translates to, we can write it in the following form. Let me go to the next page that it's easier to write. So we have delta phi. Oops. By delta x plus, let me rewrite this. T, just call this 5t, this is partial derivative with respect to t, that's equal to 0. So then we can again rearrange this. So we get delta phi delta x is x t plus phi of t equal to 0. Okay. Now this is nothing but gradient of phi. Okay. And xt is just a speed, right? Because we want to speed in the sense the speed at which x moves, but we know that this speed is always going to be along the normal to the surface or normal to the contour. So we can always say x t equal to some speed function f, okay, and n hat, where now n hat, it's not easy, it's very easy to see that n hat will be proportional to this. This is the normal, right? Why would this work? Because phi is nothing but, phi equal to 0. If you look at the level sets of phi, right, the gradient is always going to be perpendicular to the level sets at every point. So that's why gradient of phi will give you the normal. So we can then write, instead of xt, we replace it with some speed function. So phi t plus gradient of phi, some speed function f n cap equal to 0. Or if we, after some rewriting, we can always, come to this form, phi t plus f gradient of phi. So this actually gives the equation of motion of phi. Okay. Given that x has, so if x moves, what is the corresponding change in phi? This is what basically this represents at some level, because f here tells you the speed function which corresponds to x, where the motion of x and y points. Okay, so that's what this is the relationship. So we will use this. This is what is typically used to rewrite everything. So there are other quantities also involved. So we can define curvature. So curvature turns out called kappa is given by the following expression: phi xx minus 2 phi xy. Again, these represent partial derivative with respect to x and y, right? So it's the notation typically for x by y plus. So, or you can also rewrite it as del dot phi. So this is nothing but this is basically del dot n, normal to the curve, gradient, the divergence with respect of the normal. Okay, so this again can be derived. So we won't go into the derivation on how we come to this. This you can take this as a definition of the curvature. Okay, del dot, rewrite this is not clearly written, del dot. Okay, so these key quantities that we would run into when we are using level set formulations for active contours. So we can now look at the geodesic active contour. So which is basically the improvement on the Snake's algorithm that we saw earlier. So first we begin with the definition of an image edge function. Okay, image or image edge indicator function, generally denoted by this. Can use 1 plus gradient of smooth version. I'm just going to, I will be some star. Since I star is nothing but a smooth version. Okay, so you will have some Gaussian filter involved with I. Okay, so I've just not indicated it there. So it's some edge function, right? So its value when the value of the edge is very high, when the gradient is very high, this function will have a low value. And if it's when the image is smooth in those regions, this will have a higher value. Okay, and the smoothing is done to reduce noise. Okay, because we have this sometimes, if you use a simple Gaussian filter, we can get rid of some of the noise. And so in general, this function will take lower values at image boundaries compared with other regions. So we'll also define the level set function phi in terms of the signed distance function. So how do we do that? We do phi of x equal to, you can think of this as the minimum distance y belong to s. Okay, so if it's inside, there's a negative sign. It's 0 if it's on the boundary. Okay, so this delta s denotes the boundary. This is inside the boundary, and if it's outside, again, this is the squared Euclidean distance you can think of, or the norm, two norm, right? Just the Euclidean distance. Typically, let's hold on 1 second. Not the squared Euclidean distance. I think I must have. That was a mistake. This is just a two norm. Right? So just a straight distance, correct? So now we have this x here x belongs to s out, which means you are outside the boundary. Okay. So if you are, let's say, doing some organ segmentation, so everything inside the organ will get a negative sign. Everything outside the organ will get a positive sign, and on the boundary of the organ you get 0. Okay. So and x, this denotes the Euclidean distance between x and y. Okay. So this is called the signed distance function. Okay. And what, like we mentioned, the idea is that phi of x equal to 0 will give you the segmentation contour. So we also want to look at the energy, right? Or the energy functional. What is the energy functional? So for this problem, the energy functional written in terms of phi. Okay. So typically we would have written E in terms of C, the contour, right? So now, because now we are embedding the contour in phi, we'll write it in terms of C. We'll write it in terms of the um, um, phi itself as a function of phi. So we over the image. Okay. So here this delta function is basically, this is just some approximation of the delta function, right? Continuous approximation of the delta function, or differentiable, say continuous differentiable approximation, right? This is called the smoothed direct delta function, right? Again, gradient is the delta is the gradient operator. Okay. So what does this integral do? All it does is it calculates the line integral of the h function. Okay. Calculates the line integral of the edge integrated function along the zeroth level set of phi. Okay. So this is so this basically in this they used to call it the geodesic active contour, because from the geometric perspective, what the energy function does is to find a minimum length curve. It's called a geodesic curve of image in the image I. But then it's just not any distance; it is weighted by the gradient. You can think of it that way. Gradient weighted. So why does this work? Because let's say you have a curve which is on the edges of the gradient of the image, right? Let's say you have I'll just draw the usual box, and let's say you have an organ, right? Let's just use something. Let's say you have this organ. So if you draw a curve which sits right on this edge of this organ, let's say, okay. Now here the gradient will be very high. So if you calculate a gradient weighted distance, which is what this is doing, if you do a gradient weighted distance along the image edge, right, then that would correspond to a certain distance, which will be either maximum. You can treat it either maximum or minimum. Okay. So you want that, right? Because you want your curve to be on the edge of the object. So this is a kind of a metric which is derived from the gradient of the image. So it's also referred to as the geodesic active contour. It's some distance metric that you get based on the edges of the image. Okay. So if you write down the Euler-Lagrange equations for this particular functional, then we can write in terms of the level set formulation, right? So we can write this as delta phi over delta t is equal to, that we saw this gi, right? And then gradient of phi, there is a kappa plus gradient of g I dot with gradient of. So this kappa is nothing but called the curvature, and we can write it as the divergence of this particular case. Okay. So we have started off from the level set formulation to, of course, I haven't walked you through the actual derivation, but this is better off. There it is given in the publication. I'll put the reference out in the forums. So you can practice on that. There's also another way. I mean, you can work with the way the way the snake's derivation was done. You can work with the contour itself, write down the functional in terms of the contour, and then get the Euler-Lagrange equations, and from there, then substitute embed the contour in level set function. You get the corresponding level set formulation. Okay. So this this is your geodesic active contour, and by solving for this phi or time till convergence, we can actually propagate the curve. So in this formalism, the advantage once again is that you have the level set, so you can have multiple objects that you can segment simultaneously. You don't have to keep track of individual points or worry about self intersections, etc. All of them are taken into account. Okay. So but still, the point is that it still depends on the gradient. Okay. Still depends on the gradient. There is some curvature dependent terms that gives it some speed, there's the smoothness aspect, etc. But still depends on the gradient for propagation. Correct? Not the gradient of phi, but I'm more talking about the g, the term g. This actually is a function of the gradient, right? So we of the gradient of the image. So still it has problems with local minima, etc. Because if you have a particularly noisy image, even if you smooth it, that is going to be a issue. So just in case you were wondering, why would we do this? I mean, you still have the same issues cropping up again and again, the local minima problem. See, in the context of let's say medical image segmentation, especially if you're going to have some user sitting there and doing it, this is a better way of doing image segmentation rather than drawing by hand. So so you can always um, initialize the contour close to the boundary. That can be, but it can be rough, and then this particular formalism can be used to converge to the boundary. So since there is a expert user involved, especially in the context of medical image segmentation, it's a very useful tool to have if it's been programmed properly. So the other technique, which is again widely used and very popular, is called the Chan-Vese segmentation, or active contours without edges. Now, its variational formulation is from something called the Mumford-Shah model. So we will take a look at that also briefly.